In today's class, we shall discuss operating systems for embedded applications and embedded appliances. Obviously, there would be special requirements when we are considering embedded systems. We shall start with reviewing the general characteristics of operating systems before going into the specific needs of embedded systems. What is an operating system? Operating system is that layer of software which exploits the hardware resources of one or more processors which is there in the embedded system, or for that matter any general purpose computing platform. Therefore, it provides a set of services to system users, because system is making use of hardware resources through that software layer which is your operating system. OS manages memory, primary as well as secondary memory and I/O devices. Small, simple embedded systems usually don't have an OS. Instead, an application consists of an infinite loop that calls modules or functions to perform various actions in the background, because it's a common flow with different functionalities to be catered to. And interrupt service routines handle asynchronous events in the foreground. This is the basic structure for the more common systems. But on the other hand, if we really have a complex functionalities to support, then in that case we really need to have an OS. The basic model of these kind of simple embedded systems software, management software, is basically referred to as foreground background systems. So, the structure wise, this is a general while loop, because this software is expected to run forever, which has got the different modules, and these modules gets invoked within the while loop. Asynchronous events which are generated from the external environment are handled by the interrupt service routines. So, this is the basic structure of a management software, when we really do not need to manage multiple concurrent tasks. For complex applications which supports a multitude of functionality, we need mechanisms to implement each functionality independent of others. That means these functionalities will not be linked to each other through say procedure calls. So, they have to be implemented independently, and but still we need to make them work cooperatively. If this is the condition, then we really need an OS to manage that embedded system. And we had already seen that external world has got concurrent event stream or data stream. So, if we need to deal with concurrent event or data stream, we require multitasking, because with each stream we need to have a special functionality associated. And in multitasking system, CPU switches from one program to another quickly, so that it gives the appearance of executing all of the programs at the same time. In fact, we have a same processor, and on the same processor these tasks are being time shared, and these tasks are actually independent modules, and these therefore functionalities are getting implemented or realized through independent modules. So, a simple example of multitasking is here, where you have got a telephone answering machine. It can record a phone call, also at the same time it may meet the user's control panel inputs or the requests, and say for example user has picked up the receiver. So, that is a external scenario which it needs to cater to, as well as it needs to record a phone call as well, and these two can be considered independent concurrent tasks, and that is to be managed by the OS resident in this telephone answering machine. So, what are the different kinds of multitasking systems that you encounter? One is cooperative multitasking. Each program can control the CPU as long as it needs it. It allows other programs to use it at times when it does not use the CPU. That means the other programs get the CPU and can do the task only when one of the programs is not using. So, it is a complete cooperation with a complete knowledge about each other, which may not be always true. Side by side, you have got preemptive multitasking. In preemptive multitasking, a process which is in execution or each program which is in execution can be interrupted, that is preempted, and another process can be scheduled to run in its place. And in this condition, OS provides each running program with specific time slices. So, each program runs for its time slice and then it is preempted out. Okay. It is not that a process will complete its job or task within a time slice allotted. It will require possibly multiple time slices to finish its task. Now, when these processes are running concurrently, they may have different characteristics as well. When we talk about periodic tasks, it means that tasks have got a specific period with which they arrive and they are to be serviced. If we consider a simple decompression task for decompressing a video, then that task arrives at each frame time interval. If we have 30 frames per second or 25 frames per second, then these tasks would arrive at 40 millisecond interval. So, this is an example of a periodic tasks. Now, when a process is periodic, it may have other processes in the same OS which are also periodic, but their period can be different from that of a particular periodic process. So, if our OS needs to handle multiple processes which come with multiple periods, we actually encounter what is called multi-rate tasks. And all these tasks are in a way concurrent, because they have to be in state of execution at the same point of time. It is not that one task will be finished, then only I can cater to another task. There are also synchronous and asynchronous tasks. A task which is spawned by an external interrupt or an external user action would be typically an asynchronous task, and that needs to be catered to in this scenario as well. So, all these things together make the problem of multitasking more difficult. Let us take a simple example of a compressor which is compressing data. So, you have got uncompressed data and there is a compressed data as output, and this has to work in time, so that you should not miss any of the input data which is coming in an uncompressed form. Now, if you look into the overall thing, that depending on the character, and if you are using a compression table and if you use a variable length coding scheme like Huffman coding, then a character would give rise to data of a particular length, but that length is not same for each and every character. So, that problem needs to be handled. So, what we say that the input, the data may be received and sent at different rates. So, there are two processes which are managing the reception and communication. So, these two processes are working at different rates and they need to cooperate such that no input data is really missed. So, time for packaging and emitting output characters should not be so high that input characters are lost. Okay. So, this puts in a constraint on the compression scheme, and these processes have to cooperate so that the compression can take place in proper order. Now, let us look at with this background, let us look at the fundamental issues of the OS. We shall base our discussions primarily around considerations of an embedded system. So, first what happens when you power up an embedded system? So, typically there is a power on situation, and if there is an OS in a power on situation, you execute what is called a basic input output routines, which may be part of ROM. ROM may be flash memory as well, we had discussed this otherwise also, and this memory initializes and examines the system hardware. In most of these embedded systems, there is a power on self test block which checks the initial, when it boots up, it checks the hardware. Typically memory test is performed in order to ensure that the embedded system does not give rise to an unsafe state or a kind of an erroneous situation because of the hardware fault. So, if it detects a hardware fault, it would abort. So, basically what we are looking at in terms of the processing sequence, the moment the power is up. So, typically you do what is called decompression or boot loading. This is basically your basic IO routines and the OS, which is part of your ROM or your flash is loaded onto the RAM for faster execution. Okay. Then you go into what is called this BSP or board support package or OS initialization, and then only the control gets transferred to application code. What is this BSP or OS initialization? BSP is a component that provides board or hardware specific details to OS for the OS to provide hardware abstractions to the tasks that use its services. And BSP is specific to both the board and OS for which it is being written. In fact, this can be configured also for the board for which it is being written. Okay. And if you see what it talks about is it provides board and hardware specific details to the operating systems. So, the basic component of the BSP is a startup code, and we had already discussed the startup code for a raw system and what kind of functions it would support. So, it basically initializes all the components of the system, does the memory initialization, does the clock setup, and set up various components like cache. And BSP also contains typically drivers for the peripherals, which now becomes memory resident. So, these BSP or the board support package forms a very important component for all operating systems which are targeted for embedded appliances. And for each appliance or the target card, you may need to configure your board support package for a particular OS. So, for example, if I am talking about ECOS, ECOS is a OS targeted for embedded appliances, but for a particular card, I need to properly set the board support package so that on that card or the target system, ECOS can operate properly. Then the control obviously gets transferred to the kernel, the OS kernel. OS kernel is the most frequently used portion of OS, resides permanently in main memory, that means in the RAM area, and even if we are implementing a kind of a virtual memory between flash and a RAM, possibly we won't like the kernel to be part of that. Kernel would be typically locked in the RAM area of the embedded system. It runs in a privileged mode because it supports the system's functions. So, if you remember ARM processor, ARM had various modes, of which the privileged modes are system mode. So, the kernel on an ARM would run in privileged mode, and it responds to calls from processes and interrupts from devices. These processes could be the application processes. So, they can make the system calls to make use of OS services. So, what are the responsibilities of kernel? Kernel's basic job is to manage processes. In fact, all processes are created by the kernel. In fact, they are deleted or killed by the kernel as well. Since there are many processes and we are talking about a multitasking system, and therefore, what is needed? The kernel needs to manage what is called context switching. alternating between the different processes or tasks. This related to this is this concept of scheduling. When we are context switching, which process or task should run next? This is the principle of scheduling, and kernels implement a variety of scheduling policy. Then we have critical sections, providing adequate memory protection when multiple tasks or processes run concurrently, because there may be shared resources. If there are shared resources shared by two or more processes, then access to the shared resources have to be disciplined, so that one of them is really using the shared resource. That job is also handled by kernel. And there are various solutions dealing with critical sections, and the solutions differ from OS to OS. So, now we are talking about multitasking and processes. So, let us formally look at what a process is. Process is a unique sequential execution of a program. Now, if a program, even in a general purpose system, is same program, if it is being executed by two different users, we actually shall have two different processes associated with the same program. Even the same program instantiated into two different processes by the same user will also have distinct existence. So, each process therefore has got an execution context. Okay. So, all information, this execution context is collection of all information the operating system needs to manage the process. Okay. And what are the different process characteristics? One would be period, that is a time between successive executions, because we said that there can be periodic processes. Associated with the period is rate, inverse of period is actually the rate, and in a multi-rate system each process would execute at its own rate. So, this information is important for the kernel as well, because kernel schedules the processes through context switching. Okay. So, this is one aspect of the information about the process. In fact, all this information about the processes are stored in what is called a process control block. Each process has got its own process control block. This is the OS level data structure which holds the pieces of information associated with a process. Okay. And the process has got different states: new, ready, running, waited, halted, etc. And what are these states depends on, again, the definitions each OS really adopts. In a generic sense, when a process is admitted, it becomes a new process. A new process may not be always ready to run. After some transformation, meeting some of the requirements and the demands of the new process, it becomes ready to run. When the process is actually in execution, its state is running. When the process is waiting for some external input or access from the device, its state is waited. Okay. The process can also be halted, okay, for some reason, and it can be also put to different kinds of other states. In fact, in a general purpose system, a process can be moved out of the memory and put to the hard disk, waiting for its time to come. So, there may be variations of these states that we have talked about. So, this process state information is stored in process control block. Then the program counter points to the current instruction of the process which is being executed. Okay. So, that will be stored in the PCB. Why? Because when there is a context switch, this PC value has to be restored. Then also the CPU registers, which captures the state of the process, and also the CPU scheduling information, priority and scheduling parameters, for which the period as well as the rate can be important for the OS as well. It also has memory management information. We had already talked about in the context of memory that your memory can be organized in terms of pages or segments, and there has to be page table for each process. So, that pointers to the page table becomes part of your PCB. Also accounting information as well as I/O status information. That means which I/O devices, if any, this process has been allocated to it. If it is using a file system, the list of open files, etc., because this records the resource usage information, resources other than that of CPU and memory. So, if you look at typically a process state transition diagram, this is a generic diagram. A process is in ready state, from ready it goes to the executing state. If it is needing data, so it goes to the waiting state, and then again it can come back to the ready state before it gets scheduled. In fact, the OS actually schedules processes which are in ready state. So, therefore, all such processes join what we commonly call a ready queue, and from the ready queue OS picks up the process which is to move into the executing state, and this process is also known as dispatching. There are many operating systems which also support tasks or concurrency beyond the level of processes. Okay. So, what we say supports multiple threads of execution within a single process itself. Okay. Because what is a thread of execution? A thread of execution is a sequence of instructions being executed, and many of the OSs support multiple such sequence of instructions to be managed concurrently within the boundary of a process. So, under those conditions, and what happens? An executing process is divided into threads that run concurrently, and thread becomes a dispatchable unit of work. What is dispatchable unit of work? A schedulable unit of work. What I told you is that if something is a ready queue, from the ready queue, when we put that into an executing state, it becomes the process of dispatching. So, if you look into this model, then what we really find? For a process, I have got a PCB or process control block, and along with the process there is what is associated? An user address space, that the address space of the process. Okay. And in this address space of the process, threads live. Okay. Threads are concurrent sequence of instructions, okay, concurrent threads of control. So, you have got with each thread, just like PCB, a thread control block as well. Okay. And what is interesting and important to note is that each thread can have its own local variables, because it is following own sequence, instruction sequence. So, for each method it invokes along a thread, there will be local variables, there will be parameters passed to those methods, there will be return addresses corresponding to those methods. So, each thread will have its own stack, okay, a user stack. Each thread will have its own portion of the user stack. Okay. Now, apart from the user stack, there will be also the kernel stack, because kernel stack, what is kernel stack? Kernel stack is a stack which is not really resident in the user's address space, not strictly in the user's address space. It is in the address space which is being managed by the operating systems. So, let us say if this thread is under execution and an interrupt occurs, the interrupt service routine would be a process outside the boundary of this process. Okay. So, when that transfer takes place, the information, the current state of the thread has to be saved. Where will it be saved? It will be saved in the kernel stack and not in the user stack. User stack will typically maintain the local variables, parameters corresponding to procedure calls. In fact, lightweight processors or threads are ideal for embedded computing, since these platforms typically run only a few concurrent programs. So, the application level concurrency is expected to be handled more through the threads, okay, and concurrency within programs become better managed. Because you can understand also why should it be better managed, because the moment I switch from one thread to another, what happens? The amount of information that I need to change is much less, because my PCB, that is program control block, is remaining same, and that is why switching between thread to thread is much faster compared to switching between processes. And that is the reason why you will find all these OSs which are targeted for embedded applications do support multi-threaded processes. Obviously, related to all these things is context switch. So, what is context switch? Context switch is CPU's replacement of the currently running task with a new one. Okay. Now, here you need to save the old context and restore the new one. And so, the actions what are involved in a context switch are: current task is interrupted, processor registers for that particular task are saved in a task specific table. In fact, these information is typically you will be in PCB. In fact, PCB has to be saved in a task specific table, and the task is placed on the ready list to await the next time slice. That means next time when the OS schedules that task. So, task control block stores memory usage, priority levels, all this information, and new tasks, registers and status are loaded into the processor. Where from they are loaded? From the PCB of the process which is currently being dispatched, and then new task starts to run, and all these things involve changing the stack pointer, the PC as well as program status registers. So, you can understand that all this context switch obviously involves an overhead in terms of the instruction cycles which are involved for this job. Let us look at simple ARM instructions, because there are supports in the processor also for facilitating this kind of a context switch. The interesting thing to note is these are all multiple memory access instructions. In fact, multiple blocks of memory is accessed. So, in this case, the register R0 to R14 is being saved in space pointed to by R13 in ascending order, okay. That is depending on the post operator that is being associated. Now, what is the interesting feature of this? When these multiple memory transfers take place through an instruction, these process cannot be interrupted by an interrupt, and that is absolutely essential. When a context switch takes place, the context switch actions should not be interrupted by an external interrupt. If it gets interrupted, then actually there will be an inconsistency, because another process block comes into the picture, because your interrupt service routine would correspond to another process. In a standard processor, you need to disable the interrupt before you can execute this multi-byte transfers, because your PCBs would occupy multiple memory locations. One reason why ARM provides this kind of multi-byte transfer or multi-memory location transfer instructions is to facilitate this kind of context switch. And the other thing is that the same thing happens when you are loading a new process, okay. So, let us look at the sequence of instructions, how it works out. You get the address for pointer for the PCB of the new process, okay. Then you load the next context block in R13, okay, because that is where it should point to, the pointer, stack pointer. Get your status register and the PC, because that is from the location you will be getting. Then get the status register, you have to load the SPSR currently onto the from R0. Then you get the registers, load the registers, and then move the R14, basically the current PC would be the value from the link register, and so your new process gets ready for execution. So, this is just a sequence of codes for loading a new process. This type of code will be part of the kernel, And you see that your processor also supports variety of these instructions, these multiple memory move instructions to facilitate this kind of actions. So, this is what is context switch, and context switch always have some kind of an overhead. So, if you need to move small number of bytes for a context switch will be faster, and that is precisely why context switching involving thread is faster than that involving processes. So, when a context switch occurs, obviously when the time slice expires, then it can be driven, actually it would be driven by periodic hardware interrupts from the system timer. And during a clock interrupt, the kernel's scheduler can determine if another process should run and perform a context switch. In fact, when such an interrupt occurs, which comes into play is a scheduling routine of the kernel. Okay? And this scheduling routine finds out from the ready queue which process to run using variety of scheduling policies. If this scheduling routine becomes complex, that also introduces overhead. However, this does not mean that there is a context switch at every time slice. If multiple time slices are allocated to a process, there will not be a context switch at each time slice. And preemption is what? We are already talking about preemption. It means that currently running tasks can be halted and switched out by a higher priority active task, and no need to wait until the end of the time slice. This is fundamentally important. Okay? Preemption, if it is really preemptive scheme, then I can do a preemption even when the time slice has not expired. Okay? So, we had already talked about preemption, but let us try to understand now preemption in the context of exact operational mechanism. That is, preemption means forcing out a process even when its time slice has not expired. So, context switch overhead, we had already have a idea about it, and therefore, frequency of context switch depends upon application. Overhead for processor is the amount of the context switch, is the amount of time required for the CPU to save the current task's context and restore the new task's context. And overhead for system is context switch is the amount of time from the point that the task was ready for context switching to when it actually swapped in. Okay. So, this is the two kind of time we are looking at. This is the time when there is a decision to context switch and the time actually consumed by the processor in saving and restoring the context, and this is the time from the point where task becomes ready to actually the task being swapped in. So, there are these two overheads. Obviously, we would like to have this frequency of context switch minimum, so that this overhead is also minimum for an embedded appliance. So, in fact, system context switch time is a measure of responsiveness of the system, and time slicing, a time slice period plus processor context switch time is exactly the switching time that may be there between the two processes. That means, when a process is in execution, it is allocated a time slice. Next time another process can come into being only when the time slice has expired and the context switch has taken place. So, this time altogether measures that time. Preemption is mostly preferred because it is more responsive. Why? Because you do not wait strictly for the time slice to expire. You do not wait strictly for the time slice to expire, you only pay for the context switch time. And in fact, if you look into it, this gives you also an idea of what happens when an interrupt occurs. Interrupt is what? Always a context switch when our OS is managing the interrupts. Okay? So, the context switch time is actually the time required for saving the registers and loading the new registers, and therefore, that response time gets determined by this time period. In fact, if you remember ARM architecture, when I talk about FIQ, we had a copy of the registers. So, under those conditions, when we are doing a context switch, that many registers need not be saved and loaded. I have a fresh copy of them, and therefore, for that mode or that hardware signal, the response time will be much less compared to other modes. So, now at context switch, the OS routine schedules the things. So, what is a scheduler? Scheduler is that part of the operating system that decides which process or task to run next. It uses a scheduling algorithm that enforces some kind of a policy that is designed to meet some criteria. Now, this criteria may vary. One of the most important criteria would be CPU utilization. Keep the CPU as busy as possible. If a process is doing an active, it is waiting, and currently no processes are running really on the CPU, then there is a CPU is wasting time. Throughput is maximize the number of processes completed per unit time. Turnaround time, minimize a process's latency, that is the time between task submission and termination. Okay. Now, even if we maximize the throughput, the turnaround time may not be minimized, because it depends on how the processes are being dealt with. Response time is minimize the wait time for interactive processes, and real time would be that specific deadlines must be met. We had already talked about hard and soft deadlines, and those must be met. So, when we are looking at the real time, we may suffer from the problem of low throughput or maybe less CPU utilization in order to meet the real time constraints. Okay. So, all these criteria, it is not that all these criteria can be met simultaneously by following a policy. A policy determines which criteria are to be met for the purpose of scheduling. Standard scheduling policies which you find in most of the computer systems and the OSs are first come first serve. Then you have got the shortest job first, schedule processes according to their run times. Obviously, this is extremely difficult to do because you really do not know the run time of the process a priori. And this whole thing is based upon also what is called priority scheduling. Your shortest job first is a special case of priority scheduling. It means processes can have associated with priorities, and the high priority process will be scheduled if it is in the ready queue. So, priority scheduling assigns a priority to each process, and those with higher priorities are run first. But obviously, these kind of a scheme scheduling policies cannot meet our real time requirements. So, real time scheduling would be different and scheduling policies would be different. In fact, the most fundamental characteristics of a real time OS is the scheduling policies that the OS follows to meet the deadlines. What are the characteristics of real time systems? Let us have a quick review. Event driven, reactive, there is a high cost of failure, we must meet the deadlines. There will be concurrency and multi-programming because there are multiple concurrent streams in the external world. There may be also standalone, there is also standalone continuous operation without any kind of user interventions. Reliability and fault tolerance requirement, I would like that to run reliably. So, and also predictable behavior. We should not, because depending on the system load, the scheduling of the processes can vary in a general purpose OS. But I would like to have for real time OS a predictable behavior. The processes should get scheduled predictably so that the deadlines can be met. So, let us look at some examples, and with reference to the examples we shall understand how the constraints emerge. So, we are all familiar with control systems. This is an example of a very simple control system. You have got one sensor, one actuator control system. So, this is a reference input, this is a basic controller computation, and so your input comes in is an analog input which gets to analog to digital converted, this is a reference input, and this is the output of the plant which you are trying to control. So, you have these two inputs for the control law block which implements a control algorithm. It would produce the control output which would activate the actuator for controlling the system. This is a very simple generic control system model. Now, these constraints, if we are implementing this, then there would be timing constraint on this. And how does this timing constraint comes in? Timing constraint comes in because your input is being sampled at regular intervals, okay, and you are taking control action in response to that sampled input. So, what we say the basic operation is set timer to interrupt periodically with period t, and at each timer interrupt do analog to digital conversion to get y, compute control output u and do digital to analog conversions and do. This is the basic functions which happens, okay. And so, your control law is implemented where? On a microcontroller like say PIC, okay, and you have set the timer on the PIC to interrupt, so that this control action takes place at regular time. And what is required is that this action is to be done satisfying the constraints, timing constraints. So, what we say, t is called the sampling period and t is a key design choice. It may be seconds to milliseconds, because at the same time there may be other processes running which may take the user's input for controlling the plant, maybe setting the temperature, okay. So, when we are scheduling, these routine must meet the deadline. What is the deadline? Deadline is given by the period of the sampling. So, this job is a periodic job with the deadline determined by the period. I should not miss any input sample. Then we have multi-rate control systems. Let us consider an example. What we say is a helicopter flight controller. So, a typical helicopter flight controller it will have sensor. Let us say this is just an example. At each cycle, so 1 by 180-second cycle, validate sensor data and select data source. If failure, reconfigure the system. So, I am taking data at this sampling period, but I might not really like to have the control being worked out at the same frequency, okay, because control output can be generated in a slower rate, at a slower rate, because I would like to maybe look at the inputs over a number of sampling periods to decide upon a control action. So, the control action may be generated for every 6th cycle. So, therefore, the whole system becomes a multi-rate system, because you are sampling the inputs, you are checking for the fault of the inputs at a particular rate, and you are generating control action at a different rate. This is a basic difference between the first system, which was doing the basic control action at the sampling period itself. Then we can have an hierarchical control system. This is a typical air traffic flight control hierarchy. Here, when the operator is interfaced with the system and is working, the sampling rates may be minutes or even hours, okay. And when you come down at this level, the physical plant sampling rates may be seconds or milliseconds, okay. And what is happening here? You basically take the various inputs to a state estimators, and on the basis of that you decide upon the control action. So, each of these control layers or the control actions have to be executed at multiple time periods. The timing constraints are multiple, because all of them need to satisfy your sampling intervals, and they are hierarchical and they are not independent, because one is based upon the other, okay. So, in this case also we have got a multi-rate but hierarchical system. So, the issue is that when we are talking about OS managing all these things, it means that it has to manage processes with respect to multiple deadlines, and further requirement is that they are all periodic processes, because you are sampling at fixed period at multiple levels. Signal processing systems also has got various constraints associated with it, because they are also sampling the input. I cannot miss a voice sample. If I am sampling the voice at a particular rate, I must compress satisfying that sampling rate. So, response times can range from a few milliseconds to a few seconds. Let us look at an example radar system, okay, which is a very common defense based applications, okay. So, here what you are doing, you are tracking, you have to track, depending on the radar input, you need to track. So, all these things and these data goes to the DSP. So, if you look into it, this is a separate DSP processor, this is a separate data processor, okay. and this data processor is providing the signal processing parameters to the DSP. So, if you have a OS, then OS is managing what? OS is managing both DSP as well as your data processor, and it needs to schedule processes at the two processors at two different rates depending on the timing constraints the system imposes. Okay. Now, this data processor also needs to take care of the control, because your radar may be moving from one direction to the other direction. So, this is how what I was trying to illustrate, that how the different kinds of timing constraints emerge from the real life requirements, okay, and OS needs to meet these kind of timing constraints. So, what will be the process parameters if this is the kind of scenario? First, what we say, release time of a job, the time instant the job becomes ready to execute. Then you have got absolute deadline of a job, the time instant by which the job must complete execution. Then you have what is called a relative deadline of a job. What is relative deadline? Relative deadline is a deadline minus the release time. Okay. Then you have got response time of a job. What is really response time? The completion time minus the release time, because this completion time, if I am really satisfying the deadline, would be before the deadline or just coincident with the deadline. And therefore, each job Ji is characterized by its release time Ri, absolute deadline Di, relative deadline Dj, capital Di, and execution time Ei. Okay. So, if you remember the other examples that we have seen, there would be jobs with multiple, there will be multiple jobs, and each job will have different parameters. For the simple control scheme, there will be same parameter, but when we are looking at multi-rate controls, hierarchical controls, or even radar processing system, the jobs will have different parameters depending on the scenario. So, this is an example that this is where a job comes in, this is the release time, this is where I have got the job deadline, and this is the time period where the job gets executed. Okay. We schedules it here and it gets executed. So, it has got a response time which is 6, because 9 minus 3 gives you the response time. Then the tasks can be periodic. So, we associate a period Pi with each task Ti, and Pi is the interval between the job releases. Sporadic and aperiodic tasks, which are tasks released at arbitrary times, and we distinguish between them because a sporadic has got a hard deadline and aperiodic typically has no deadline or a pretty soft deadline. So, this is an example of a periodic task. So, you find the task gets released at regular intervals, and what I have shown is the deadline coincides with the release, because these tasks related to these data must be finished before the next job arrives, and this is true for majority of the sampling driven tasks, because before the next sample arrives, the previous sample should be processed. Now, when we schedule real time task, an important issue becomes the schedulability. It is the ability of the task to meet all deadlines or not, because it is not that all tasks can be admitted to meet the deadlines. Latency is the worst case system time to events, okay? And stability in overload means the system meets critical deadlines even if all deadlines cannot be met. So, there is a distinction, and you meet those deadlines even when load on the system is high. Now, these are the parameters by which you can actually evaluate the scheduling policies, and schedulability is an issue on the basis of which you will decide, or an OS decides, whether to admit a task or not. What are the different scheduling policies? We shall look at these policies in more detail in subsequent classes. We are just introducing the policies today. Cyclic executive, where all work tasks are fit into a common period and executed in a non-preemptive fashion. If there are multiple periodic tasks, if we can compute LCM of these periodic tasks, find that period and then schedule all these tasks together in that period so that they execute in a non-preemptive fashion, we get a cyclic executive policy. Rate monotonic is a preemptive scheduling where tasks are assigned priority based on rates or periods. Okay. In many cases, preemptive can actually mean that when a task arrives with a higher priority, I may interrupt currently executing task even when the time slice has not expired. Deadline monotonic is another preemptive execution where tasks are assigned priorities based on fixed deadlines. In fact, variation of this is earliest deadline first or EDF. Preemptive scheduling where tasks are assigned priorities dynamically based on closeness of current deadlines. Okay. Related to this, you have got least laxity first. It is again a preemptive scheduling where tasks are assigned priorities dynamically based on the amount of slack time that remains between time needed to complete work and time to the deadline. Depending on that gap, you decide which task to be scheduled. And all these scheduling policies, because the issue comes up is which scheduling policy to select. Okay. So, you would like to have high utilization and still guarantee hard deadlines. Okay. Now, there can be a conflict on this criteria, because if you are trying to meet the deadline, you may not be able to admit jobs to increase your CPU utilization. CPU may be waiting for a while so that you can meet the deadlines of periodic tasks or even for aperiodic tasks with deadlines. So, the other objective comes in is provide first aperiodic response and still guarantee hard deadlines. This is the most difficult thing, because you might have scheduled the task, but now suddenly an aperiodic task arrives and you need to give a first response time. Then there should be low overhead, because your scheduling should not consume lots of time, because this is a fundamental problem. Because if the scheduling itself consumes time, then you will be missing deadline because of your scheduling policy. Okay. So, you cannot have a very complex scheduling mechanism. Okay. So, what we say, the dynamic policies tend to have higher overhead, and since they may reorder the run queue at each scheduling decision. Okay. So, each time a process arrives and you need to reschedule the processes. The moment you are rescheduling the processes, what happens? There is a time spent, because you have to reorder the queue. Reordering the queue at least means manipulation of the data structure, because in that queue you have kept your PCBs. So, that data structure has to be manipulated. So, that introduces overhead. You also have an overhead because of calculation of the policy that you need to do. Okay. So, this gives us a very basic introduction to OS targeted for embedded systems. And what we should understand is that this scheduling in terms of the real time constraints is a key problem. Okay. And what we have looked at the basic policies. We need to analyze these policies to understand these implications, and these analysis we shall do in the next class. Any questions? Yeah.
So, if you know that any process cannot meet the deadline, then we miss that process.
Yeah. So, the whole question is whether if you know that a process does not meet a deadline, what shall I do with the process? See, if you remember, we talked about schedulability. Okay. Now, when we are admitting a process, our OS can check for its schedulability. If it can be scheduled, then only the process should be admitted. Otherwise, I need not admit that process. That means that process does not join the ready queue. The process may be started, the OS checks for its schedulability. If it cannot be scheduled, then it need not join the ready queue. So, it will be in a kind of an suspended state. Okay. Fine. Any other questions?